Hi everyone. So for this video, I'm going to talk about kinetic molecular theory, and this is kind of going to be a nice little continuation of gases, because in all the previous videos we talked about these equations like ideal gas law, Dalton's law of partial pressures, which did a great job on explaining how you can take a system of gas and be able to figure out things about pressure and volume and moles just based off what you know from the beginning. But when you actually start to think about it, you have to ask yourself, why do these work? You know, chemistry gets really complicated really fast when you start to get into it. So, like, usually when you learn equations or you learn some new theorem, there's a lot of assumptions that go into making that equation or making that theorem to avoid all the complications. So, with the ideal gas law, it's called ideal for a reason because you have to ignore certain things. And kinetic molecular theory sort of goes about giving you some assumptions on how gases should behave in a way to avoid a lot of complicated math, and a lot of like the very tedious calculations. So to actually start talking about those, there are really four assumptions, and I wrote them all out here. They all are seemingly simple, but they have some complexity to them, and there are reasons why these all have to be true that I'll talk about on the next slide. But the first assumption is that the volume of the particles themselves, and I'll actually rewrite that here now that I'm thinking about it. So the volume of the particles themselves have to be about zero or negligible. What that means is that in the container itself, the particles basically don't exist, but they exert their like force and their pressure on the container. The reason this matters is because we can just treat the volume of the system to be the volume of the container. We don't need to worry about how much gas there is really, because those particles really don't like add up to anything important, really. It's kind of a weird one. Like this one, I would say the first one's kind of the weirdest one. And like I would say just remember it, like your gas is basically zero volume, and that's fine. Your volume will always just be the container itself and however big that is. So kind of along a similar trend, number two is that the particles themselves cannot exert any attractive force with other particles or with the walls itself. The reason this one matters is more so dealing with how we think about like energy transfer. So like, or even volume itself. So like think about it like this. If when you heat up, like let's say water, it doesn't instantly turn to gas, right? Even though you are giving it the energy to do so, the reason you have to give it more than you would expect is because you have to break some intermolecular bonds, or sorry, intramolecular bonds between the water atoms themselves. So your energy isn't going to just making the particles move faster and become gas molecules. You need to break some bonds or break some attractive forces between atoms. And so with gases, it's kind of the same thing. If you were to heat up a gas, it would be really hard to figure out how much of that heat went into like breaking up these interactions versus actually making the gas move faster. You definitely could. It's just really tedious and really annoying. So if you make this assumption, you can then like do all the math to assume all of this heat is only making the gas move faster. There are no bonds that are forming. There's nothing at all that's occurring in the system that could take away energy that I'm putting into it. So basically with two is just saying that all the heat that's going into the system is just to make it move faster, and that these particles are just like independent of each other. They don't know that they all exist, basically. And so with three, this one's more so for people who have taken physics or know a little bit of like mechanics. You don't have to. It just helps, I think. But with number three, it says that all the collisions are perfectly elastic. And what that means in mechanics or classical sense is that when two things collide, typically you can even test it yourself, like clap your hands. You make a lot of sound and your hands hurt and maybe they feel a little bit warmer. Like there's always a transfer of energy that occurs when two things collide. That can be sound, can be light in some cases, can be radiation in the case of like particles. So naturally you're going to lose energy every time that happens because the energy that was stored in this kinetic collision is going to convert it into sound or whatever I just said. Um, so over time, that means that your system would get cooler, right? It would cool down since those particles keep hitting, they keep losing energy that's going off somewhere. So to avoid that, this just says that when they collide, they just keep going on and they have the same energy they did before. It didn't change anything. Is that true? This is not true. But again, it's just to make the math easier. None of these are actually rigorously true in all cases. They're true in some cases, not in all the cases. It's just easier to imagine that they are true. And then the last one, I gotta rewrite this in a way that's with less symbols. I'm sorry about this. Um, so no, when the last assumption of kinetic molecular theory that's really important to know is that the average kinetic energy of the system of the system depends only on temperature. So I got wow, that's bad. So what this means is that if you make your gas hotter, the gas particles on average will have more kinetic energy, which therefore means they'll move faster. And I'll explain why we can say this definitively in a second, but I'll also explain why we say the average kinetic energy. Just try to keep in mind for right now, we're talking about a container filled of like you can't even say a number big enough to describe how much gas there is in it, like in terms of the particles themselves. So you really can't describe the kinetic energy of one of the system itself because there's so many particles in it that all will have slightly different kinetic energies. It's kind of like saying, like you can talk about like I guess rain, like weather or temperature. Like you can say that like, oh yeah, it's like 80 in Texas or 90 in Florida. But like that depends on where you are. Like some places will be warmer, some places will be cooler. I guess a good example is the United States as a whole. You can say, oh yeah, on average it's like 50 degrees in the United States, but like some places will be a lot warmer. Some places will be a lot cooler. So like we talk about the average of all the pieces, which is what kinetic energy average means in this case. Um, and I wrote down some of these points in the next slide. Um, and also, I think if this is helpful, I'll post these as well, in, like a PDF. I think it's just easier than making you guys like write this down. So like, I'll let me know if that's helpful. I'll do that too. But yeah, I just wrote down here why these are true. So like with number one, this is said that the volume of the particles themselves is about zero and we can ignore it. Just remember how crazy like chemistry is in terms of like the quantum mechanics of it. Particles are so small. Like the nucleus of an atom compared to like how big like the electron cloud is ridiculous. Like so much of an atom is just empty space. And then you compound this with like a a ridiculous amount of gas particles that also have a stupidly high amount of empty space. Like the particles, not that they don't exist, but like they really don't contribute anything in a meaningful sense in terms of like volume because like, they're just so small. So the size of the particles themselves compared to like how far apart they might be, like they basically don't really matter. And it's basically like infinitely far away. So they kind of are zero. Again, I'm nerding out. You don't need to know that. Just keep in mind that the particles are basically zero volume. And it's just because they're so far apart from each other. Um, and then that kind of ties into the whole attractive thing. They're so far apart that they hardly can attract each other. But also, if they did attract, they would create a smaller volume, right? Because if you think about like gas wanting to occupy this whole cup of water I have, if they're starting to attract each other, they'll compress a little bit and start to aggregate more. So if they don't attract, then it helps to imagine the gas occupies a full volume. Again, I'm nerding out because I love chemistry, but just keep in mind, all that really matters is that the particles don't attract one another or the walls to prevent any aggregation or to prevent any like adhering of the gas particles in one area. They should be equally as likely to be in the top, in the bottom, the middle, wherever in the container. It should not matter. And then with the collisions, we talked about this, they need to be perfectly elastic, otherwise the energy would decrease and the container would cool down over time. We don't want that. We just want to imagine this is a perfect gas container. You put it in, it's got enough heat, it's just doing its thing. It's doing the expansion or the contraction. Awesome. We're gonna stay with that. And then with the like I'm gonna say this one very quickly because it doesn't matter until you get to like college chem really. But when you talk about like energy, we usually just say like, oh yeah, if you like heat something up, it moves faster, which like is true. You know, if you heat up gas, it doesn't move faster. But there are other ways that like molecules can move besides just like left and right. So I give you an example. If you imagine like carbon dioxide, which has this sort of structure, if you put in some heat, you know, it can definitely move faster left and right, which would be your translational kinetic energy. But if you heat it up, these bonds actually aren't rigid. Like that's the beauty of chemistry when you get to like quantum mechanics. Bonds aren't a fixed thing, or they don't exist in one location. So these bond lengths actually always are changing and doing stuff. So this CO bond here is actually stretching, it's vibrating, contracting like this all the time. And even the angle of the bond too, like this right here, is actually rotating also. So now you have rotational energy, vibrational energy, um, even like some like flexing of the bond like this. Like it's really cool stuff. Um, but at least in terms of wanting to imagine that gases are simple and make the math as simple as possible, because you can't possibly figure out how much heat goes into translational versus rotational. Like not right now, at least. I don't think it's worth it to worry about that stuff. But I think it's nice to help show you like what actually is happening and why we say these things, not that they're true, but why we say them to help make chemistry a little bit easier for right now. So at least for right now, kinetic energy is dependent on temperature, and temperature makes gas particles move faster. That's the gist of it. That's all you really got to know. Um, and like this is really like the only main equation that like matters for like kinetic molecular theory. Um, it comes up again in thermodynamics, which is really cool. But it's basically just that your kinetic energy is 3/2 RT, which again, it makes sense. We just said that energy or the kinetic energy depends only on temperature. So it makes sense that in the equation, it only has two constants, 3/2 and R. So what this means then, in a rigorous sense, if we go about like thinking of like what problems you get on this topic, if you have two gases, so two gases at same T will have the same kinetic energy. Average, I'm going to say average. The reason I keep emphasizing the average is because we're going to get into Boltzmann distributions later on in this video. And those are a really nice way. It is beautiful. I can't, it's not, it's beautiful. Okay. Um, they basically show you at different temperatures or at different weight gases how that impacts the distribution of energies. Because again, think about gases like temperature in the United States. Like we can say on average it's like 50 degrees today. But if you're like in Florida compared to like to Denver, you're gonna have a very different experience. Just like some gases will have a very different experience on if they move faster than other like particles of gases within the same container. So this is really the main equation you need. There is one more, and like I'm just gonna write it. You don't need to prove it. I'll show you where it comes from, but it's we use U for this. It's weird. It's still velocity, but it's called the root mean squared. So the root mean squared, which basically mean, and I'll break this down. I'll give you the equation first. It is the square root of 3RT over M, where M is the mass, but this mass is going to be in kilograms, which is not weird. It's kind of weird for like chemists. I guess it's weird because it's a capital M, which is like molar amounts. Like I thought that would be a molar mass, but whatever. So make sure you're in kilograms, not moles by accident. Um, And yeah, basically, where we get this term of root mean squared from is the fact that one, we're talking about an average kinetic energy. I'm not asking you the kinetic energy of one particle of gas. Otherwise, just give me the velocity of it or whatever. Use that. But when we talk about a whole aggregate, a ton of gas particles, we want the average velocity. So that's where the mean comes from. This comes from the fact that we're going to be using the average velocity of all the gas particles. Secondly, the root and then the squared part. So again, you don't need to know physics for chemistry for the most part. One aspect about velocity is that it is a vector quantity, not a scalar quantity. Vector quantities are just things that care about the direction you're going. So if you, let's say that you're driving home from school and it's like an 8 mile drive, right? The distance you travel is 8 miles, right? Because you just went 8 miles back to your house. However, your displacement might not be, because what displacement cares about is the direction you went. So maybe you were going south, or maybe you were going like southeast or something like that, in which case your direction impacts the sign of it. Because of that, velocity is the same way. Velocity is a vector. It cares what the direction you go in. For instance, 5 miles this way and 5 miles this way are the same speed, like 5 miles per hour. Those are the same speeds, but because they are going in opposite directions, one is positive and one is negative. So because of that, you can have negative velocities. You can't take the square root of a negative. We don't want to get imaginary like values for your velocity. That just wouldn't make sense. So instead, what you have to do is square the term. That way, all your values, because think about it, if you square something, if it's positive, it's still positive. If it's negative, it becomes positive then. So you turn all the negatives into positives and you take the square root. Because if you square root a number, if it's positive, it'll stay positive. So the way to basically convert all your negatives into positives and use it. Again, does this matter? No, I'm just a nerd and I love talking about this, okay? That's the gist of it. I'm a nerd, guys. But I just want I want you to be able to look at a word or look at a term that's used in chemistry and be like, okay, I don't really know how to use this, but like I know what it probably means. Like that's kind of the beauty of chemistry is just looking at something and say, okay, what could this probably mean, right? So I'm gonna at least show you where this comes from. Really, all you need to use is just kinetic energy equation. So kinetic energy, for anyone who's taken physics or stuff like that or just knows it, it is 1/2 mv squared, right? But we already have up above here that the average kinetic energy is 3/2 RT. So instead, let's rewrite this as the kinetic energy average has to be equal to 1/2 m. Now I'll use u squared because that's just what the average velocity is called for some reason. I don't know why. If anyone knows, please tell me. I would love to hear it. And then we just say, okay, this term also equals this term up here. We'll just let them equal to each other. So we have 3/2 RT. Awesome. Now we just multiply both sides by 2. That cancels out. We get that m is equal to, sorry, my bad. We get that m u squared has to equal 3RT. You see where this is going. I divide both sides by m, and then I take the square root. And that's how we get the root mean squared value of the root of 3/2 RT over m. Again, does this matter? No, but now if your teacher ever asks you to show it, or if you just want to like know it, now you have it, basically. Um, and the only reason I wanted to touch on that a little bit is because I do want to show you like how like root mean squared is used in like an actual context in chemistry. So for that, we can talk about Boltzmann distributions. This is kind of where we get into like the really I think the cooler parts of like gases and stuff. Because now we say, okay, if you put a whole container of gas and you heat it up, even though it has a certain amount of energy, not every particle of gas will have the same energy. And that's sort of like the funkiness of chemistry. So with these Boltzmann distributions, I just want to show you how changes to it will impact how the graph looks. So before I actually get into that, I think it'd be really good. I gave you one here. So you know that temperature will impact um, the velocity because that's what these graphs are. They're a graph of the velocity of these particles relative to how many particles have that velocity. So like you notice here, let's say for T3, for example, this green one right here, the majority of the gas particles have it at this energy, at that speed. Sorry, that speed. Um, but then for T2, this is the most popular one. That's the speed that most of the particles are at. So you know that temperature will impact the speed. Based off what we just talked about, what would you guess will be the second graph? We're gonna do it right after, but if you just want to think about it, I think it'd be helpful. But what you notice here is that as you increase the temperature, because this I put it as T1 is the hottest temperature, T2 is the second hottest, T3 is the coldest. What you notice is that as things get hotter, so as you go from T3 to T2 to T1, the peak of each gas, or I guess each temperature, decreases. What this means is that as things get hotter, they begin to basically occupy more states. They begin to spread out more. And even though you have the majority of your gases at this hotter temperature, they do still exist across the whole spectrum. And that's what comes up a lot in chemistry is distributions. It's the fact that even though something is unlikely, it's not impossible. So even though it is very unlikely for a gas at this T1 temperature to have the exact same velocity as a gas in the T3 temperature, it's not impossible. So what you cannot say is that all of the particles at this T1 temperature move faster than the particles at T3 temperature. That's not true. Not all of them. The vast majority definitely do. But what we have to say is that the average kinetic energy or the average velocity increases. So what you have to say on like an exam, for example, is as temperature increases, this leads to an increase in the average velocity, right? And remember, when we're talking about velocity, because we assume that all the heat goes into kinetic energy, this therefore means that we also get an increase in the average kinetic energy. So nothing is like changed about chemistry, right? If you heat something up, it moves faster and it has more energy. That's absolutely true. But what we're doing now is we're actually looking at the whole distribution. We're saying, okay, what is actually happening to this gas? Is all of it as like fast as the other particles? No, not all of it, but the majority of it is way faster. Because look, even going from what's it called? Even going from T3 to T2, we see this drop, right? All that drop means is that it's less precise, right? In this one, we have like almost all of the gas, like a ridiculous amount exists at this speed, right? At T2, we have less of the gas at this one speed, but it is a faster speed. So overall, as temperatures increase, the graph looks wider. And shorter. So it widens and shortens. I'm gonna actually let's move this over a little. It gets wider and shorter. Awesome. So time for the last one. And if you have a guess, please give it. But the other thing that matters is your mass also. If you want a reasoning, look back to kinetic energy. We're changing the velocity here. You can't change the mass of a gas particle in theory by heating it up. You and actually that's it. I'm not gonna confuse anyone. But you can change you can change the gas. There are tons of gases. I give you some examples here of noble gases. So you have xenon, argon, helium. And what you notice here is we should always try and match things. So xenon looks a lot like T3. So looks a lot like T3, T2, and T1, right? What's different about them in terms of their mass? Helium is super light. It's basically like it's just two hydrogens, basically, right? It's a very light molecule. Argon, a bit heavier, a bit bigger. Xenon, very heavy atom. So what you see here is that something as its mass decreases, the velocity is increasing, right? Which makes sense because let's say I forgot to say one thing. We're gonna assume same temperature for all the gases, right? And this is why we have to do that because as we said in the first slide, the kinetic energy depends only on temperature. So if I'm at the same temperature, then I have to be at the same kinetic energy. So same temperature equals same kinetic energy. And what does kinetic energy equal? So kinetic energy is equal to 1/2 mv squared. So if I'm at the exact same kinetic energy for all these gases, then the only thing that's going to impact their velocity is their change in mass. So as you go from a so as you go from a like heavier to a lighter atom, this decrease in the mass is going to lead to an increase in velocity. So we get a similar pattern here where instead of trying to worry about the temperature, we get that as the mass decreases, sorry, no, my bad. As mass increases, as you go from like helium to ar, actually, no, we're gonna keep this consistent. As mass decreases, as you go from like xenon to argon to helium, this is gonna lead to an increase in the average velocity. And again, velocity is what really impacts kinetic energy. It's a squared term. So a small change in velocity has a massive change in kinetic energy. So if you increase the average velocity, you get an increase in the average kinetic energy. And now what we get is a slightly different relationship where instead of increasing temperature, when you decrease the mass, your graph looks wider and shorter again. So this is something I think that everyone can definitely reason through, and you can talk through this on an exam. I think if you're allowed a cheat sheet or like a little note card, it'd be good to probably write down this graph and this other graph as like an example to hold on to and look back on. But remember, all of chemistry revolves around energy. Does something increase or decreases energy? Or if energy is constant, what else can be changing? In the case of temperature, increase in temperature directly leads to an increase in energy, and we can figure out how that energy impacts other terms like velocity. In the case of mass, though, we're keeping energy the same across all of these gases. But what that does is it allows us to mess with the terms that impact the energy. So in this case, if we can increase or decrease the mass, this will lead to an increase or a decrease in velocity. So like I think this is like one of my favorite like aspects of chemistry. I wish I took like college thermodynamics to really see where this like comes from, like in the math and the quantum mechanics of it. Um, but I think this is a really great tie-in that takes all the like the math we've been doing across the past couple of videos and gives some more theoretical like framework to look at gases and to understand how gases behave and why they behave the way they do. Um, so yeah, I think probably I'll do one more video. You can see it up here. Like I want to do one video on effusion and diffusion. It's not super important. Like don't worry about it. I'll talk about it in that video. If you have any questions at all about Boltzmann distribution, the kinetic molecular theorem, you'll notice I didn't do any practice problems in this video. You really can't do many, and I really wanted to emphasize these two graphs since this is really the only practice problem you could get. I guess in theory, you might be able to get a question where it's like, oh, here's the mass of a gas at this temperature. What's its average velocity? But again, that's just like plugging and chugging. I don't think that's really helpful for me to just like do the math for. I think these more so explanation based questions or these longer questions of, oh, what are some of the points of kinetic molecular theorem and why is this true? Like why do the particles not attract? Or why do we assume that, right? So I think with this one, this kind of like the first video or like the set of like theorems where you should really just sit down and try to talk it through to yourself. Like ask any question that comes to mind and write it down and see if you can figure out the answer or see if you can like reason through why this happens. Like go back through, erase all my work and just go through this mass and just say, okay, if I'm going to increase mass, how would that impact energy? And why would that impact it in that way? And why does temperature matter here? Ask yourself those questions. And I think you'll be really well prepared if you ever get this question on an exam. Um, and yeah, I think I'm gonna end the video there. Thank you so much for watching, guys. Hopefully one more for gas, and then I'll just upload all these in like a big bunch on YouTube. So fingers crossed I can do that soon. But yeah, thanks for watching. Hope you have a great day.